So the last speaker in this session before we have the poster flashes is Vivi Arief, and she will talk maybe about similar kinds of analysis for Australia.
Thank you, Fred. So my talk will be kind of similar with Eeuwijk somehow, but I will talk about Australia rather than the Europe. So this is the Australian grain growing regions. So it's divided into three main regions: the north, which is comprised of New South Wales and Queensland; the south, which is the South Australia, Victoria, and Tasmania sometimes; and the west part, which is the Western Australia. So this is the north. So it's a high soil fertility, it's tropical to temperate climates, and has a summer and winter dominant rainfall. So the Queensland and the North New South Wales is a summer dominant rainfall, and the South New South Wales is the winter dominant rainfall. With the south is a diverse range of soil, generally low in fertility, is a temperate climate, and yield depend on the reliable spring rainfall. For the west is a low soil fertility, Mediterranean climate, and yield depends upon the good winter rainfall. So the National Variety Trials, or the NVT, is the largest independent grain crop variety, according to their website, and evaluate commercial and the near to related varieties for 10 major crops, including wheat. So they do about 650 trials per year, about 300 sites across Australia, and these sites were chosen following extensive consultation with the stakeholder groups. They are reporting the single site analysis and the 5 years multi-environment trial in the website. So we focus on the yield data, which is the wheat main season. We have data for 8 years from 2015 to 2022. There's 1,027 trials, so roughly about 112 to 164 trials per year. There's 433 unique genotypes, 17 to 85 genotypes per trial, on average about 50. And then they use a row column design with 3 replications. So this is how the trial look like, some of the example of them. So the size is varied, and this is something that we do something before we do the analysis. We put that one into like missings because it's some very low. And they also sometimes missing the whole row of the whole column that we also remove before the analysis. So we do the single site analysis. We do a comparison between using SPAT and AS-REMO. So again, the design row column, so we put row and column as a random. And then we fit genotype as fixed to get the blue and the weights. And then we fit genotype as random to get the variance component and heritability. So for the SPATS model, we managed to fit 1,026 trials. There's one trial with only 2 columns that not running. With AS-REMO IR1 model, that's basically run 7 models and select based on the AIC. And we managed to fit genotype fixed. We managed to fit 1,024 trials. With 2 trials, it's not converging. And then genotype as random, we can do all the 1,027 trials. So this is the comparison of genotypic variant. So that's from the AS-REMO. That's for the SPAT. That's basically kind of nice. With they're not much different on the estimated genotypic variant for a single trial. That's for the residual variance. So there's all here. And the SPATs tend to have a smaller, but the median is kind of the same, but the SPAT have a bit less kind of outliers. The heritability, again, there are not really difference between the SPAT and AS-REMO. This is the genotypic effect. So we have the blue and the black. So again, this is the correlation for the blue and the black within each trial. So that's between the 1,024. I think they have a common 1,024. So that's basically kind of a highly correlated. So based on that result, the next analysis will be done based on the result from the SPATs rather than from AR1 AS-REMO. So this is basically the mean yield from each of the trials. So that's for the north, the south, and the west. So as you see, the north has the highest mean yield, and the south and the west is about the same. And this is the distribution from 2015 to 2022. So there's a quite strong year effect. So the 2016, 2019, 2019 is quite low overall in the whole country. And then 2016 is quite high. And then 2022 is also high in all trials in all countries. So this is the heritability distribution. Again, this is the north, the south, and the west. So they are about comparable. There's a bit of a different variation in the year. In 2020, there's some of the trials that really have a low heritability for some reason, the same in 2017. So the next step is we're going the multi-environment trials analysis for this. So this is the relationship. So this is the genotype. The diagonal is basically the number of genotypes in this year. And then this will be the connection, the common genotypes across. So the more years, the connection of the common genotypes is getting less. So the north have 283 genotypes, the south have 314, the west have 210, and then this will be the common one between the west and the south. And then there's the common one between the west and the north, which is the smallest one. So the common genotype between west and north is the smallest. And this is basically showing the genotype and then where they are tested. So when it's gray, then they are tested in that trial for that years. This was split into years for the north, the south, and the west. And you can see that if there's a tested on the west, they're unlikely to be tested in the north and vice versa. There are also some genotype that tested across multiple years, and some that only happen like single year or 2 or 3 years. So this is to show how the genotype and the region related. So this is from the data is directly come from the NVT website from 2005 to 2023. And this is basically the sub-region. So the region of the north is split again into sub-region, the one in the south and the one in the west. And you can see that there's a bit, this is based on 267 release cultivars yield information. So if you see that the north is kind of a bit different from the south and the west. For the genotype itself, this is the wild Chapman derived line. So there's wild Chapman and there's the wild Chapman is the parents of each of them. And they are bred for the west region. The purple one is the AGA Gregory derived line. So there's the parents and they always have AGA Gregory. They breed from the northern region breeding program. So they are really adapted to the north. And this is basically the CIMID introduction. So it's a Borlock 100, Secondamine, Sunmas, and Samtot. They have the CIMID background. Secondamine is basically introduction from CIMID that released in Queensland. So they are performing relatively better in the north rather than the west and the south. For the meta-analysis, we do the two-stage analysis. So we have the blues and the weight from the spots. We do the weight as an inverse of the prediction error variance. And then we also remove the trials with the heritability of 0. There's not many, there's a couple of them. So we end up with 1,022 trials that were retained. This is the model that you've been basically seen whole morning. So we just fit the trial as fixed and then everything is random. This is the variance component. So this is for the north, the south, and the west. So it's stacked. So this is the genotypic variance. There's the G by Y. There's the G by L, G by Y by L, and the pool residual. So we have the pool residuals, and that's why the residual doesn't have the standard error. There's the standard error. So the genetic variant look almost similar to the three regions. There's the north have mostly the highest phenotypic variance and with the highest G by Y by L. But if we convert it into percentage of the total to the phenotypic variant, then basically the north has a very small genetic variant. It's only half of the one in the west. So it's about 12%, while the west have 25% contribution of the genetic variance to the total. The west doesn't really have much of the G by Y, and the G by L is not large in all the regions. Again, with the G by Y by L, you see the absolute value of the variance component that look very large on the north, but the contribution to the total is about similar to the other two regions. So again, we model the trialing efficiency like you've already done, so there's the same formula there, but we do have the residual here, so we can have the R, and we also have the genetic repeatability calculation. So there's an assumption in this modeling that the variance component was estimated without error, and the variance component can be used for modeling are transferable to similar trials, and there's no restriction on the resources. So for the current 5 years metadata analysis, we have the number of sites per year is about 40 on average, and because of unbalance in the testing, that each of the genotype is on average tested 2.4 years, rather than 5 years. So that's basically the result for the north, the south, and the west. So that's for the 1 year. We try 2 years, 3 years, and up to 8 years. We start from 1 to 50 sites per year. We also try with the number of replication from 3 to 5, but they are overlapped, so we remove it from the thing there. So increasing the number of replication doesn't really help in this case, but increasing the number of years does have an effect, and that was basically the genetic repeatability for the current 5 years. The multi-environment trial analysis is somewhere around here, and as expected, the west has a bit higher than the north. We also do the 5% LSD. So again, that was, as expected, the west is very kind of tight there, and that's the north. And from all this is basically we are over testing. So we probably only need about 10 to 15, but most of the trial running in about 40 per year. But yes, it cannot be changed due for other reasons. So a summary basically is the quality of single trial. There's some heritability of single trial. It varied from year to year from trial per trial, but they're kind of quite good. It's about 0.8. And then the north has the more variability than the west as expected. And then this was translated to the trialing efficiency. So the west has more better trialing efficiency than the north. And yes, there's probably an improvement that can be made by increasing the number of years, but the number of location or site basically already large enough that need to be changed. So as acknowledgement, this was funded by GRDC for the funding through Invita project and also the supplying the entity data, and that's basically Xi Xiao is the student that extracting some of the data from the website, and Mark is the one that gives the variety list to be displayed with the CIMID, wild culture, or AJ Gregory derived line. Thank you.
Okay, you are the first speaker within time. So we can have 2 short questions. Marcos, we rely on you.
Thank you for the presentation. I was wondering, I mean, there are 40 locations on average every year, so it looks like
40 sites.
Yeah,
yes.
it's like a lot of opportunities to reduce, whatever reasons that it's not that maybe happening. But do you see also opportunities to identify among those 40s the ones that actually could be left out, if that could be possible, before?
We have another thing that doing more a grouping of the trials, which is yes, but left up that site is not really what they want. The GRDC and VT people doesn't want to reduce the number of sites, so we're just showing that they are over tested, but yes, it has to be stay.
These are jobs. Okay, Mark.
Mark? Maybe a quick one. In both of the previous talks, there was a lot of discussion about locations and years. I wonder if there's any appetite in these networks for thinking about when you could use the knowledge of the environmental covariables to design management strategies that may be a way of accelerating the whole process by decreasing the number of years of testing that are required to build confidence in your decision making.
There will be talks about this later in the program.
Yeah, that was the other part of the project is try to get the environmental type and environment covariate to sort of get the G by Y by L